Hello, and welcome back to the course on quantum mechanics. We are still on the fourth chapter for this course. So far, we have discussed about the quantum orbital angular momentum. And these are some of the properties and equations involving quantum orbital angular momentum. So, their components are not compatible with each other, meaning their uncertainty relations are given by this, and the total angular momentum is compatible with its components and with the Hamiltonian. And these are the eigenvalue equations for the total angular momentum L squared and one of the component Lz. So the angular moment, the z component, the angular momentum is actually quantized. It's a multiple of h bar. And we discussed about raising and lowering angular momentum operators, L plus and L minus, defined by this. And lastly, the raising and lowering operators actually just increases the value of m by 1. So it raises the state to a higher state, or it lowers the state to a lower state for the raising and lowering operator. You get here, it's m plus and minus 1. So for this lesson, we will now focus our attention on the second type of angular momentum. The quantum version of that is the quantum spin angular momentum. So an electron, again, both has an orbital angular momentum and a spin angular momentum because it's spinning along its axis. So for the spin quantum numbers, we just replace L by S. Instead of L and M sub L, we have S and M sub S. But unlike L, which can only have integer values, S can have half integer values. 0, 1 half, 1, 3 halves, 2, 5 halves, and so on. And similarly, the values of M, the quantum number, the magnetic quantum number Ms is just from negative S to positive S. But it can now have half integer values. So the spin angular momentum is also called the intrinsic angular momentum because it is unique to a certain particle or to a certain system. And by this definition, we can now call the orbital angular momentum as the extrinsic angular momentum. And because it's an intrinsic property, it can be used to classify particles. So for instance, if the S value is 0, an example particle of that are the pions or the pi mesons. If S is equal to 1 half, sometimes we call that spin 1 half. Those are the particles that make up matter: electrons, protons, neutrons, and the subcomponents of protons and neutrons, which are quarks. So they're all spin 1 half. And for spin 1, an example of that are photons. For spin 3 has delta particles, and for spin 2, the gravitons, the proposed mediation particle for gravitation, of course. So again, the S value, the S quantum number for any given particle is fixed, but it can change value if the system is perturbed. So we'll discuss more about this perturbation in the last chapters of this. So similarly, the equations for spin angular momentum are just exactly the same as the orbital angular momentum. You just change the L's to S. So you change the capital L to capital S, you change the small L the lowercase l to lowercase s. So still, the components of the spin angular momentum are incompatible with each other, but the total angular momentum commutes with its components and with the Hamiltonian, and this is now the eigenvalue equation for s squared. Instead of l plus 1, h bar squared eigenvalue, you have s plus 1. And this is the eigenvalue equation for sz. So similar with orbital angular momentum, spin angular momentum is also quantized, but it's a multiple. Instead of a multiple of h bar, it's a multiple of h bar over 2, or 1/2 h. So similarly, we also have raising and lowering operators, s plus and s minus, and a similar formula. The raising operator raises to a higher state, and the lowering operator lowers the system to a lower state. So if you recall, the orbital wave functions are given like this in Dirac notation, and the spin wave function are given as this one. So the complete time-independent wave function of a particle is actually a combination of the orbital wave function and the spin wave function. So since these are all probabilities, the total probability is essentially the multiplication of the probability, the orbital probability, and the spin probability. And you get something like this. So the complete wave function, time-independent wave function of a particle is a combination of the orbital wave function and the spin wave function. So what happens now if you have two particles? They interact, but they have different spins. So you can actually add their spin angular momentum. So just the total spin of two particles. So for example, you have particle 1 with spin s1 and particle 2 with spin s2. So the total spin can have values of s1 plus s2, s1 plus s2 minus 1 until the absolute value of s1 minus s2. So these are the possible values if these two particles with different spins interact. And their spin angular momentum, the total spin angular momentum, is just the addition of the two angular momentum, the spin angular momentum of particle 1 plus the spin angular momentum of particle 2. And similarly, if you try to get the lowering and raising operator, by the way, I would like to emphasize, I forgot to emphasize in the last video, that the raising and lowering operators, the ladder operators, are not physical quantities. They are operators, but they do not represent physical quantities. So similarly, you just add the ladder operator for particle 1 plus the ladder operator for particle. So the general two-particle state will now be a multiplication of the wave function, the eigenfunction of particle 1, and the eigenfunction of particle 2, and the linear combination of all those possible values. So see here is just a coefficient called the Clebsch. I don't know if I pronounced it correctly, but that coefficient. Okay. So let's have an example of the spin of an atom. So the simplest atom is the hydrogen atom. It's composed of a proton in the nucleus and one electron orbiting the nucleus. So the electron is a spin 1/2 particle. Similarly, the proton is also a spin 1/2 particle. So if we try to solve the spin of the hydrogen atom, then for an electron, if s is 1/2, then its value of m is -1/2 to +1/2 in integer steps. So there are two values of m, 1/2 and -1/2. So the state 1/2, s is equal to 1/2, m is equal to 1/2. That's the spin up na state. And the second state, which is 1/2, -1/2, that's a spin down state. So similarly, for a proton, it also has a spin up and a spin down. So the number that you see here just corresponds to the number of the particle. The 1 corresponds to the electron, 2 corresponds to the proton. Now, if you use the formula, so the possible values of the spin of the hydrogen atom is either S1 plus S2, so 1, until absolute value of S1 minus S2 or 0. So a hydrogen atom can have two spins. S is equal to 1 or S is equal to 0. So when S is equal to 0, there's only one value of M. M is equal to 0. So since there's only one value of M for this S, then there's only one state. And that is why it's called a singlet, because there's only one state. And this state is actually anti-symmetric, or the proton and electron here have anti-parallel spins. And this is the singlet state. In terms of the wave functions of the electron, the ones with number 1s here, and in terms of the wave functions of the proton, the ones with number. For S is equal to 1, so the values of M are -1, 0, and 1, meaning it will have 3 states. That is why it's called a triplet state. So these states are symmetric, meaning the proton and electron have parallel spins. So these are the triplet states. This is the state 1, 1, the highest state in the ladder, and this is the middle state, and this is 1, -1, the lowest state in the ladder. Now, take note that in the singlet state, you cannot apply the raising or lowering operator here. Or you can apply, but you will get 0 because there's no other state. If you raise this, then you get 0. There's no state above this. There's no state below this. Okay, so these are the triplet states. Okay, let's have an example. So let's try to find the spin eigenvalues and eigenstates of delta particles. S is equal to 3/2. So if S is equal to 3/2, meaning the values of M is from -3/2 to +3/2 in integer values. So you'll have 4 values, -3/2, -1/2, 1/2, 3/2. So the number of M's corresponds to the number of states, so meaning there are 4 states for delta particles. So these are the 4 states: 3/2, -3/2, 3/2, -1/2, until 3/2, 3/2. So meaning, if you take the eigenvalue equation for SZ, so M sub S here have 4 values. So meaning, if you measure SZ, you will get, or you will only get these 4 values. Only 4 values are possible. The rest are impossible or improbable. So you will only get either -3/2 H bar, -1/2 H bar, 1/2 H bar, or 3/2 H bar. That is what the eigenvalue means. There are no other possible values, only these 4. And each of these values have different probabilities depending on the initial state. For S squared, so since the eigenvalue of S squared doesn't depend on M, it only depends on S, which is 3/2, then its eigenvalue is 15/4 H bar squared. Meaning, if you measure S squared, you will always get 15/4 H bar squared. But if you measure S, the total spin angular momentum, you will get square root of 15/2 H bar every time. So the magnitude of the spin angular momentum for any particle is actually fixed. That is why the spin can be used to identify or classify particles. So another example is for quarks. So quarks are spin 1/2 particles. So when 3 quarks bind together to make a baryon, such as a proton or a neutron, and 2 quarks can bind together to make a meson, such as a pion or a kaon. So assume the quarks are in the ground state, meaning it has no orbital angular momentum. So only spin angular momentum is involved. What are the possible spins for baryons and mesons? So for baryons, it's made of 3 quarks. So say we have 3 quarks. As the first quark, S1, have a spin S1, 1/2. Second one is also 1/2. Of course, the third one is also 1/2. So the combination, the addition of S1 and S2 will produce either a spin of 1 or 0. This is now the combination of S1 and S2. I made it, or there's a subscript here now, 1, 2. Now we combine this spin with this spin, and you will get what? So for 1 and 1/2, possible values of S is 1 plus 1/2, 3/2. 1 minus 1/2, 1/2. So 1/2 and 3/2. For 0 and 1/2, you'll get only 1/2. So therefore, if 3 quarks bind together, their combined spin will either be 3/2 or 1/2. For letter B, for mesons, for 2 quarks, so just similar to the hydrogen atom, 2 spin 1/2 particles. So meaning spin can be 1 or 0. So when 3 quarks bind together and they form a spin 1/2 state, that can either be a proton or a neutron. And when 2 quarks form together to form a spin 1 or spin 0, for instance, you can get pions or kaons. So for the last example, so this is the only example with the calculation. So show that for the hydrogen atom, if you act the lowering operator S minus to the state 1, 0, 1, 0 is the middle state in the triplet state, you will get 1, -1 with a factor of square root of 2 h bar. So 1, -1 is the lowest state in the ladder. So this is obvious, supposedly. If S plus acts on just a single state, the singlet state, there's no other state, so of course you will get 0. And show that the state 1, 1 and 1, -1, upper and the bottom states of the triplet states are eigenstates of S squared. Okay. So before we proceed, we need to review what are the states, spin states of a hydrogen atom. So these are the 4 spin states of the hydrogen atom. This is the singlet state, for S is equal to 0. And these are the triplet states. So I no longer place the superscript 1 and 2, but the first arrow corresponds to particle 1, the electron, and the second arrow will correspond to particle 2, which is the proton. In this case, the second arrow, always the proton, state of the proton, the first arrow corresponds to the electron. Where the spin up and spin down state in Dirac notation is just 1/2, 1/2 for spin up, 1/2, -1/2 for spin down. Now, if you, based on the formula for S plus and S minus, if S minus acts on the spin up state, you will get the spin down state, the factor of h bar. Similarly, if the S plus acts on the spin down state, you will get the spin up state. The other combination is if S minus acts on spin down, since the spin down state is already the lowest state, then you will get 0. And if you act S plus on the spin up state, then you will also get 0. Now, from SZ, from the formula of SZ, the eigenvalue equation is like this. If SZ acts on a spin up, you will get h bar over 2 spin up. The eigenvalue is h bar over 2. If SZ acts on the spin down, then you will get the eigenvalue of negative h bar over 2. This is for the negative m value spin down. Now, for Sx and Sy, I would like to emphasize that the spin up and spin down states, that we discuss here, are the eigenfunctions of S squared and Sz. And these are not necessarily eigenvalues of Sx and Sy. In fact, Sx and Sy have different eigenvectors, or eigenfunctions. So if Sx acts on the spin up, you will get h bar over 2 spin down. Sx acts on spin down, you will get h bar over 2 spin up. And for Sy, you will get this And for Sy acting on the spin down, you will get this one. So I will leave this term here as an exercise for you. You need to use the S plus and S minus relationship here. You must write Sx and Sy in terms of the raising and lowering operators in order to achieve these relations or equations. Okay, we'll be using these values for this problem. Okay, problem number 1. S minus acts on 1, 0. So 1, 0 is this one. So for letter A, the total S minus will be S minus for particle 1 plus the S minus for particle 2. So take note, this S minus operator will only act on particle 1 or the states of particle 1. And this S minus, the second S minus operator here, will only act on the states of particle 2. Meaning, if you let this act on, say, these states, this one will always act on the first arrow. This one will always act on the second arrow because I no longer place the subscript 1 and 2 here. So this S minus will act on the first arrow. This S minus will act on the second arrow. Okay. So for the first problem, S minus acting on 1, 0. So the S minus actually is this one. S minus for particle 1, S minus for particle 2. This will act on 1, 0, where 1, 0 is this thing. So 1 over square root of 2, I will take the factor 1 over square root of 2 outside. You will get up, down, plus down. So this is for the first problem. This is the total S operator, S minus operator. Sorry. The minus is, sorry. Okay. So this operator, the first operator S minus 1, will only act on the first arrows, and this operator will always act on the will only act only on the second arrow. Okay. So you will get what? You will get 1 over square root of 2, then S minus 1 acting on the first arrow. So you will actually get 4 terms here. So you will have S minus 1 acting on this, up, down, plus, down, up, plus S minus 2 acting on same states, down, up. So again, S minus will act, S minus 1 will only act on the first arrow. The S minus 2 will only act on the second arrow, or for the states of particle 2. So you use this value. If S minus acts on up, spin up, it will be equal to H bar over 2, H bar spin down. So meaning S minus acting on this will actually give you a down. So this will become a down, spin down with a factor of H bar. And for this case, S minus acting on down, that will give you 0. So the term is actually 0. For this, you have S minus acting on down, that will give you 0. For S minus acting on up, that will give you H bar down. Basically, it's down, down, it's down, down. And your final answer will be 1 over square root of 2, H bar, 2H bar, 1 over square root of 2, and then you have 2H bar down. They're both down, down, you can add them. Or if you simplify this, you will get square root of 2H bar, and the down, down state, the down state is the 1, -1. 1, -1. This is S minus acting on 1, 0. Okay. So I think you already now get the idea. No? So for example, for letter B, you do the same. So S plus and S minus will be a combination of the S plus and S minus for particle 1 plus for particle 2. And for letter B, it's obvious because 0, 0 is this state. And just do the same. You just do the same process. S minus 1 will only act on the first arrow, state of the electron. And S minus 2 or S plus 2 will only act on the second arrow, state of the proton or the second particle. So letter B is actually obvious. Okay. I will go directly to letter C. So for letter C, we need to prove that S squared act on state 1, 1. We will have an eigenvalue equation because that's the way to prove that 1, 1 and 1, -1 are eigenstates. I'm just gonna put here plus and minus 1, plus and minus 1. So if S squared acts on 1, 1 or 1, -1, we will get lambda 1, lambda plus or minus 1, 1 or 1, -1. That's an eigenvalue equation because we are trying to prove that these two states, 1, 1 and 1, -1, are eigenstates of S. So the first angular momentum vector, say S1, will something like will look like this. It will have three components, say Sx particle 1, x hat, Sy particle 1, y hat, Sz particle 1, z hat. And similarly for the second particle, it will also have the same components. X for particle 2, Sy for particle 2, and Sc for particle 2. Now, the total vector now, spin angular momentum vector now, will now be spin angular momentum vector for particle 1 and then for particle. And if we take the inner product of this vector with itself, we will actually get S squared. S dot S is S squared. And this is equal to what? So if you use these values, this vector dot with this vector, so just multiply the components. So you will have Sx of particle 1, Sx of particle 2, plus Sy of particle 1, Sy of particle 2, plus Sc of particle 1, Sc of particle 2. This is now our S squared operator in terms of the Sx, Sy, and Sz components. Wait, sorry. I made a mistake. It's actually, sorry. Our S is this one. So that product of this one itself. Sorry. It should be S1, sorry, S2, dot product with itself. 1 plus S2. This will actually be four terms. The first term is S1, that S1, that's actually just S1 squared. And second term is this S2 and S2. That's just S particle 2 squared. Then you have the middle terms. So from the middle terms, you will get actually 2S1 S2. Because that product of the S's are commutative. And this term here, now the dot product of these two. So this is Sx of particle 1, Sx of particle 2, plus, and so on. We just continue this one. So Sx of particle 1, Sx of particle 2 plus Sy particle 1, y particle 2 plus Su particle 1, Su. So you can now have the uh, form of the total angular momentum, spin angular momentum squared, S squared, in terms of the total S squared of particle 1, total S squared of particle 2, and their components, Sx, Sy, and S. So you let this S squared act on the states 1, 1, and 1, negative 1. And again, as a general rule, the operators with the power or the superscript 1, that power of superscript 1, will only act on the first arrow. So for instance, for 1, 1, this is 1, 1. So all of the operators here with superscripts 1 will only act on the first arrow. For 1, 1 and for 1, negative 1, the first arrow. And all operators with superscript 2 will only act on the second arrow because this is the state of particle. Do you do the same? I will leave that as an exercise to you. And you will actually get an eigenvalue. So S squared acting on 1, 1 or 1, negative 1 actually give you a value of 2 h bar squared 1 negative 1, 1 or 1, negative 1, depending on the state. So meaning the states 1, 1 and 1, negative 1 are eigenvalues of S squared. The total angular momentum of or the total angle, this is now the angular momentum, spin angular momentum of the hydrogen atom. It has a value of 2 h bar squared. So notice that this result actually follows from the formula. If you notice S squared, just S times S plus 1. In this case, our S here is, for these states, S is equal to 1 because this is the triplet state. So for S is equal to 1, you have 1 plus 1, 2 times 1, so 2 per square. So this is a triplet state. This is S is equal to 1. So S is equal to 1 here. It follows the original formula, eigenvalue for S squared. S plus 1 H. And that is the end of this lesson. So for the next lesson, we will be focusing still on the spin angular momentum, and we will focus on basically the most important spin particles in terms of spin, the spin 1/2 particles, the particles that make up matter. So electrons, protons, neutrons, and quarks. So that will be the focus on the next lesson. I will see you again in the next lesson.